Yeah, it has started. Ah, sì. Sì, perfetto. Okay, if you, first of all, I would like to tell to everyone to welcome to our series of webinars, to our participants of the summer school and to our teachers and coordinators. And first of all, I would like to present you, you know already very well, but one more time, it's our coordinator from University of Utrecht, Mieke Lumens. And now I'm giving to her the role of the moderator for a while. Thank you.
Okay, good afternoon, all of you. Most of you have a good afternoon. For me, it's a good morning. Well, before the actual webinar on epidemiology starts, I would like to give you a very brief introduction on how this series of webinars will continue. And for that, I'm going to share my screen with you. And well, this is so this is it. We decided to well, because of Corona and all uncertainties and not knowing exactly when we can really have the summer or spring school. Well, we've decided to start with a series of webinars. And why did we think it was important? Well, we think having this series of webinars will provide you with a common foundation of knowledge. That, well, we think we selected topics that are of relevance for all of you, for well, developing all modules. So, well, and as stated here in this slide, hopefully there will be a summer or spring school in May next year. Here in the Netherlands, things are not developing in the right direction. So I'm really hoping that May 22 will be an option. Let's hope for that. Let's wait and see. But until we get to really get together in person, we thought it would be good to have a series of webinars to make sure you all have the same knowledge. And how will these webinars be developed? Well, as you already noticed, we sent you for this first webinar some background reading materials, and we hope you had a chance to have a look at these, because these will really help you in preparing for the webinar and understanding what's being discussed well, after my introduction. And this is the first one. For the rest of the webinars, we make sure that next to having background reading materials, there will also be some assignments so that it's more an active way of presenting this information. And there will also be some tests to make sure that you really picked up the relevant information for this webinar. And in parallel, or in taking turns, we will also provide you with a series of webinars on how to actually design the modules we've been talking about. And again, that will be with the start of providing you some background reading materials. And well, since you will be working in groups on the, designing the modules, there definitely in these webinars also be group assignments. So you have a chance to, well, to discuss the theory and already put that into practice in the design of your specific module. And what we also would like to encourage you is to already get to know your group members, the people that you will be working on your module with, so that during the time until the actual summer school, we can ask you for regular updates on the progress you're making. Well, this is also stated quite easily and maybe a bit fast, but well, in the next weeks, we will provide you with more information on this so that you well, that there is a plan, that there is a structure, and that you know exactly when to expect what. So this is what we promise, and we will provide you shortly. Well, we've been thinking based on topics that are being taught at other master programs, that this would be a possible list of topics that should be addressed in these foundation webinars. So this is what we thought of. This is still open for discussion, but to give you an idea what to expect in the next month until the actual face-to-face summer school will take place. So as you notice, it's quite a long list. And well, for these first 2 months, we think one webinar per month will be sufficient, but we hope to speed up things a bit. And in the new year, so as of January, we will probably schedule 2 webinars every month to make sure that, well, the common layer of knowledge, well, is there in place when we meet in the summer school. So this is, well, the first dates. You can already note these. Today is November 4, and well, you've all been notified about this webinar, the Introduction to Epidemiology, that will be given by Professor Dario Consonni from Milan University. And then next month, Dr. Wietske Dome and myself will introduce to you the first step towards module design. And then as of January, we will start with a 2-weekly series of webinars. And as I understood, if I understood correctly, till this we'll find out what will be the best time to schedule these meetings. Because for us, well, we are
Professor Dario Consonni.
I didn't get that. So
no, it's just noise.
I'm a bit lost now. Mm-hmm. I stopped sharing my screen, and well, this is it from me for now. And I see that Professor Consonni has joined the meeting, and well, welcome. We're very happy that you are available to start this introduction to epidemiology and share it with the candidates. And I think that's it for now. So as far as I'm concerned, Professor Consonni can take over.
Thank you very much, Professor Mieke. We're happy that you are one of the teachers, the same time coordinators. And the next floor, I'm going to give to the Professor Dario Consonni, who is going to take today lecture on epidemiology. But I have one request. All of our participants, please turn off your microphone, because it's making sense. Thank you very much. And please, Professor Dario, first of all, I would like to express our gratitude to you that you agreed to conduct this lecture. Thank you. Grazie mille, Professor. And floor is yours. Professor, we cannot hear you well. I think something wrong with the...
Something wrong with the connection.
Yeah, connection.
Problem, I guess, just...
He will rejoin. So Dear participants, if you didn't understand about the program or something, you can come back to this video and watch it again. So it will be clear, and also you can ask me in the WhatsApp, which I created for you for informal conversation. Okay, so, and please, one more time, I'm reminding you, write me in WhatsApp what is the appropriate time for you. Thank you.
Can you hear me now?
Yes, very well, thank you.
The second time it works. The first time I always have problems. So I begin to share the screen. Can you see it?
Yes, our participants,
It's coming.
please let us know. You can send some emoji that you're hearing this.
Sorry?
For me, for others, let us know. Participants.
Not visible.
Not visible.
It is visible.
Ah, okay.
Now it's disappeared. Yeah. Now we
Now,
can
okay.
see. I can see.
Okay. Can I start?
Yes. Now we can see.
Okay. Thank you. So I will start with a basic introduction to some epidemiology concepts. I start from the very basics, giving an overview of study types. We will talk about observational study types. I assume that you have some knowledge of randomized control trials. Please interrupt when you don't understand something. Please ask. Okay. So, the traditional classification of epidemiological observational studies is into three types: cohort, case control, and cross-sectional. Cohort, also called follow-up study, consists in a study in which a group of subjects with a given exposure, which is the cohort, is followed up to measure disease occurrence. So we start with exposure, we do the follow-up, and we record the outcomes. In occupational epidemiology, this type of study answer to the question, what effects does this substance cause? So the emphasis is on the exposure, on the, for example, a toxic pesticide or something else, and you want to measure the outcomes. In clinical epidemiology, this is the study who answer the question, what is the prognosis of these patients? So it's similar to a randomized controlled trials, but exposure is not assigned by the researcher. The cohort, of course, includes only subjects who are free of disease of interest. And follow-up might be very short, minutes, hours, days, or very long when you study chronic disease. So years or even decades. Is it okay?
Okay.
Okay. The second type of study is the case control, sometimes also, but rarely, called case reference study, in which the exposure frequency, but better, the odds of exposure in a group of subjects with a given disease, who are called cases, is compared with that of a healthy, that is without that disease at that moment, subjects. These so-called healthy subjects are called controls or reference. So the start here is from disease. You take diseased people and a group of non-diseased people. You collect the information about exposure. It's similar to the medical approach. The physicians see the patient and ask questions. And this study answer the question, what are the causes of this singular disease? Okay. Exposure is measured through interview. There are things that you can only know by interview, for example, smoking history or occupational history. Or you have existing data on paper and or electronic files, or you may have biobanks, biotechs with biological samples. This case control is typically a matter of confusion for people who are not familiar with epidemiology. So you can, you must think that the essence of this study is that we take all cases in a given area, for example, and a sample of the population from which cases came. So controls are best view are a sample of the population from which cases originated, and not a control group. If you think this way, you will not fall in the trap who is typical for clinicians. For example, they say the controls should be comparable to cases. This is completely wrong. Cases have a disease, so are different from controls. So you don't have to be, you don't have to have comparable controls. This confusion arises because in randomized controlled trials, we have two arms, the treatment arms, that is exposed to treatment, and the control arm. So control in this case means non-exposed. In a case control study, it means non-diseased. For this reason, in the past, someone proposed to change the name, to use a different name, case referent, but it was used especially in the Scandinavian countries. But the term control is still widely used. So be careful not to confuse controls with non-exposed. Remember also that case control study is inherently retrospective. You ask about the past. So if there is a follow-up of patients, for example, then it's not a case control study. It's a cohort study of patients. It's okay?
Yeah, okay.
Yes.
Okay. The third type of study is the cross-sectional study, when it is usually said that exposure and effect are evaluated concurrently. That is, you take a photograph of a situation not a movie like in cohort and case control study. This type of study is useful for many purposes, but sometimes, often it's difficult to say if exposure comes before the effect. So it's less good for etiology. Also, it's not always true that exposure effects are evaluated concurrently, because you ask also about past exposure. For example, smoking history. This is a study that typically used to investigate symptoms, physiological variables like lung function, or when you do biomonitoring, when you measure something in the blood or in the urine. It's not good to investigate etiology of chronic diseases. It is also called survey. It can be repeated over time. In this case, it's called panel study or longitudinal study by statistician. And in this case, if it is repeated over time, you need special statistical methods, which of course we don't cover here. So this is the classical classification. There are proposals for changing this classification because in that kind of study that kind of a classification don't cover dynamic populations. Dynamic population, as simply said, are a population residing in a well-defined geographical area. And we will see that the majority of case control studies are performed within dynamical populations. So this classification goes this way. You have, based on the outcome, which is incidence or prevalence, which we'll see shortly. If you do not have sampling, so you study the whole population, they are simply called incidence or prevalence studies. If you have sampling, for example, you take a sample of the population, you have incidence case control studies and prevalence case control studies. So in this classification, case control studies include cross-sectional studies, in particular prevalence case control studies. Okay, and note that some projects start in a way and continue in another way. So in a single project, you may have multiple study design. For example, you start doing a cross-sectional study and later you decide to follow up the cohort. So it becomes a cohort study. So remember the distinction between a cohort and a dynamic population. A cohort includes a well-defined list of subjects, who can be workers or patients or what else. There is follow-up, individual follow-up usually. The cohort gets older with time and its size decreases. Inclusion is usually defined by an event. For example, admission in a factory, presence at an accident, industrial accident, birth in a given city in a given year, diagnosis of a disease, and these subjects will constitute the cohort. Most often in chronic disease epidemiology, subjects are at risk until outcome occurrence or random follow-up. A dynamic population is a population living in a geographical area. There, you don't have a list of subjects. You have only aggregate data, usually. There is no list of subjects because every day the population change. Inclusion is defined by a state, residence. Subjects enter the population by immigration or when they birth, and exit the population through immigration or death. So every day that dynamic population changes. Size and composition over short, moderately short time periods are constant. This is called steady state. So for example, the city of Milan is the same today, tomorrow, the day after tomorrow, next month. Okay? So we have briefly covered the types of study. Now we go by illustrating measure of disease occurrence. Most occurrence measures include three elements: the cases of disease, so the number of new or existing cases, the population, so the number of people in the group or the whole population from which cases come, and time. So we have reference to a time point or interval. The product of population and time is called the study base. This is a key concept in epidemiology. So it's the population over time. And the cases originated from the study base in a given period. Okay, sometimes you have only cases. So the first measure of occurrence is the cases itself, but only in specific situations. In this situation, you use only cases. If you do time series studies, for example, to study the acute effect of pollution, since the study base, the population is the same today, tomorrow, the day after today, next month, you can only count cases and do calculation using cases. This is true also for epidemics. The population, the underlying population is the same over, at least over moderately short period. So you can use cases of COVID-19 to study the pandemic. Okay, so when the population is constant, you can use only cases. Then there are peculiar studies which are called case only, used typically in genetics and pollution, to study genetics and pollution, in which you base the study on case only. And another type is called case crossover study, which is used in pharmacoepidemiology to study accidents, pollution. It's a sort of case control study for acute effects of parian exposure. So it's a bit difficult, this topic, but just remember that if you have acute effects of exposure with vary acutely with time, you may have case crossover studies are a useful tool. Apart from these situations, it is in general incorrect to make inference based on cases only. So be careful when you have only cases. Just a couple of examples. This is it's in Italian, but it's understandable. These are the deaths recorded in London during the big pollution episode in December 52, in comparison with mortality in the same period in the 5 years before. So this is the usual mortality. And that year, you can see thousands of deaths here. Over a few weeks, you had a huge mortality. So,
excuse me, doctor.
yes.
Slides are gone.
Okay. It's okay now?
Good, we can see.
Okay, so this is an example in which the population is constant. You have an epidemic of death from pollution, the big smog in London. You see the huge increase of mortality over a few weeks. This is the influenza, the flu, which every year causes some additional death. In these cases, pollution and flu caused more cases. For people who are interested in environmental epidemiology, this is a good tutorial in the International Journal of Epidemiology, in which you see that in time series studies, the unit of study is not the subjects, but the day. So every day you have some measure of pollutant, for example, ozone, or potential confounders, temperature, humidity, and the number of deaths. So in this type of study, the analysis unit is the day. You don't need a denominator because the population is constant over the period. This is another example, mortality from pleural mesothelioma caused by asbestos. This is asbestos consumption in the UK, chrysotile, amosite, crocidolite, 3 types of asbestos, and this is the trend of mortality over the years, and these are the projections. So if all men, you see that a peak is expected after 2020. So there were few hundreds deaths that year, and mortality increases up to more than 3,000 deaths per year.
Excuse me, sir. In this slide, can I ask a question?
Yes.
So this is the cohort study, right? Or the case control that turned in the cohort?
No, this is simply we can call it a population an incident study, which is not covered by the classification you see before. It's not a cohort because you don't have individuals. Sorry, it's not a case control. It's you can. Is it difficult to classify it with the classical classification? I will call an incident study because you take.
Okay.
Could I ask
Thank you.
also the question on the same slide?
Yeah.
But how was the correlation studied here? How did you find that this amount of the disease is because of horizontal or asbestos exposure?
Okay. This is because mesothelioma is caused in practice only by asbestos. So if it were another disease, for example, lung cancer, would be better correlated to smoking. So in this case, we know that mesothelioma, apart from rare exceptions, is caused by asbestos. So it's almost a monofactorial disease. So you can visually correlate asbestos consumption and pleural mesothelioma mortality. This
Okay.
you can replicate this picture in any country.
Okay, another question again about this, but it must be correlated with the concentration of asbestos or horizontal in air or somewhere else.
Sorry?
Right? It should be correlated also with the concentration or amount in the air or in the water of horizontal or asbestos.
In the water, no, there is no evidence that asbestos in water is dangerous, but it's better to avoid it. The problem of asbestos is when it is inhaled in the lungs. In this case, you have the correlation is so strong that you can just put here the annual UK asbestos imports in thousands of tons and correlate with mesothelioma. We know from many other studies, which are cohort studies and case control studies, mostly cohort, that asbestos is a very strong cause of mesothelioma. I have to say that for mesothelioma, the worst type of asbestos is this, crocidolite. UK, Italy, Germany, Netherlands, Belgium, France, Spain, Australia, South Africa, United States, all used all this type of asbestos. So they faced a big pandemic of mesothelioma. Chrysotile is considered less dangerous for mesothelioma, but we don't have to forget that chrysotile also causes lung cancer, which is more difficult to study because for lung cancer, the main risk factor is cigarette smoking, tobacco smoking. Is it clear?
Thank you very much.
Thank you.
Пожалуйста. Now a question for you. This is a study from a neurologist in Milan. It is about hydrocarbon exposure. In practice, they mean solvents, hydrocarbon solvents, and Parkinson's disease. So they say methods, cohort study of 99 patients with Parkinson's disease, selected from 1,455 subjects. So they took 99 patients. Then they say case control study. In all subjects with positive history of solvent exposure, 188, which they call cases, matched for duration of disease and gender to the same number of subjects selected from those unexposed to solvents. What is your opinion on this paper? Just a moment. Let's see. Sorry.
No, I just want to ask because this study design is not clear for me. Because if it is a case control study, where is the case and where is control? I mean, where the case is a group who was exposure, yes, hydrocarbon.
Yeah.
And yes, and where the description of the subgroups, I can see it.
So the design is not clear because they quote two types of study.
Oh, yeah, yes.
Cohort and case control. What are cases in a case control study? Who are? Who should be? In a case control study,
The case group who was exposed or had yes.
No.
And no. Oh, okay.
Yeah.
Case group is with disease.
Yeah.
Yes.
Case
Remember
group with
this.
disease. And
Don't
control without disease.
Don't confuse this. This is the typical misconception because control is non-exposed only in a clinical trial when we are studying drugs. In a case control study, cases are diseased. Okay, so these colleagues fall in the trap. They don't know what is a case control study, so they called these 188 cases and the other controls. Completely wrong. Okay? But it was accepted in neurology in 2000.
Excuse me, can you repeat what was wrong?
Case control study, you can take cases, for example, you take Parkinson's disease.
Yeah.
100 cases of Parkinson's disease. You take 100 controls, so that do not have Parkinson's disease, maybe have, or taken from the general population, or maybe are from the same outpatient clinics, but without Parkinson, with another less severe disease. And you do the interview and you measure the frequency of exposure to solvents. So, okay, diseased, not diseased. Parkinson, no Parkinson. In this case, they called cases those exposed and controls the unexposed. So completely wrong.
Okay.
Note that they are all cases. Let's see the result.
Yes, could about the conclusions, if you will see on the conclusions, it's a little bit
The
confusing
conclusions
also.
are completely unjustified.
Mm-hmm.
So this paper should be thrown in the rubbish, to be crude. Let's see for a moment the results. Characteristic of 99 patients included in the study. So you don't have controls. You don't have subjects without Parkinson's disease. So it's not a case control study. Do they mention what is the synonym of cohort study?
Group study.
Follow-up. Follow-up.
Follow-up.
Follow-up. Okay. Do they mention follow-up? No. In the abstract, there is no follow-up. Suppose, for example, that they were interested in the prognosis of Parkinson's disease. How many die in 20 years, let's say. So they do a follow-up of the cohort and see the outcome is death. This will be a cohort of patients with Parkinson's disease. But their objective is not this, and they don't mention follow-up. So this is not a cohort study. Clear?
Yes.
So it's not a cohort, it's not a case control. It's a case-only study, but in the negative sense. It's not a formal case-only study. So they took 99 patients. They did the interview and say, okay, these are exposed, these are non-exposed. They look at age at onset of Parkinson's disease, here, 50.2 years, and non-exposed to solvent, 58.6. So they conclude that occupations involving the use of solvents are a risk factor for earlier onset of symptoms of Parkinson's disease. So if you are exposed to solvents, you get the disease before, earlier. Completely wrong.
Sorry, Professor.
Yeah.
Can we also see the screen, or we are not supposed to see, or it's only me that's not seeing this screen?
The other.
The screen, yes, the screen is visible. We can see the table.
I'm sorry, some participants, they have a not stable internet connection in Central Asia, such as Uzbekistan, Tajikistan. And we're sorry for this inconvenience, but unfortunately we cannot stop now and move to another platform. Let's just move forward, because we're recording this meeting, this lecture, and if it's not many things not clear, you can rewatch it again by the same link in the Microsoft Teams. I will upload this video again. Okay.
In any case, I will give you the updated slides. I will send to Gilles.
Yeah, thank you very much, Professor. I will resend you to all the slides which we had today. Okay, don't worry.
Okay. So this is a typical mistake, to rely only on cases, to infer etiology of a disease. This is a long known problem. It's a mistake who has been known for many years. For example, in an old book called on 1974, there was a paper on fallacies in statistical reasoning. Colton quote a study in which in the USA, some researcher collected all the deaths of US physicians in 25 years, so a huge number, and to verify if ionizing radiations were dangerous. They calculated the age at death of radiologists, which was about 60 years, and age at death of physician not exposed to radiation, which is 5 years more. Okay. So the comment is, on average, the radiologists die 5 years before the other physician unexposed to radiation. So they are saying that the radiation kill you, steal you 5 years of life. This is wrong. You don't have to do this. You have only cases. So it's not a cohort, it's not a case control because you have only death, all death. It's not a cross-sectional study, so it's not a study. A Colton comment this comments like this: the example contains a fallacy consisting in interpreting numerator data as they were a rate. We will see shortly what is a rate. And the explanation is that at that time, radiology was a relatively young specialty. So radiologists were on average younger. All radiologists, not just the dead, not just the radiologist who died. So you compare a young population with an older population. Deaths in the young population are younger than in the old population. There are other examples. The average age at death of ordinary professor will be higher, than that of assistants, because to become an ordinary, you have to be older. The same for generals and tenants, presidents and Congress members. So these are things that you don't have to do. So the conclusion was, beware of average age at death figures in the sense of numbers. They are not helpful and can be seriously misleading. So this warning, not look at cases only, is contained in many books and papers. For example, the book which usually we study, Rothman, this is the introduction, and there is another larger book. And say average age at death does not address the issue which of these groups faces a greater risk of death. When you look at age at death, you ignore all those who survive. So average age at death does not reflect the risk of death, but only a characteristic of those who die. So Rothman warning is beware of common sense. Sometimes it's good, sometimes it's not good. One should adhere to basic AP principle to avoid traps. Okay? But this mistake is repeated over time in many situations. Here we have a study on asbestos. You have mesothelioma cases. They have a cohort of cases, but they used only mesothelioma deaths. And they calculated the latency period. So this was, this is a letter we wrote against a paper from UK in which they did the same mistake. They look only at cases and calculated the latency period according to occupation and so on. So I quote this just because in the references in our letter of critics, there are many papers and books that we quote that warn not to do this mistake. It's okay?
Yes.
Yes, sir.
Okay. So sometimes only cases are sufficient, but be careful. The second measure of frequency is prevalence, which is simply, I think, a number of diseases existing in a given population in a certain moment or period, divided by total population. Prevalence indicates a state. For example, the diabetic state. For example, prevalence of diabetics in Lombardy is 2 to 4%. Is a proportion. The numerator is included in the denominator. So it goes from 0 to 1 or 0 to 10%, 100%. You can use not only for disease, but for determinants, for example, prevalence of smokers. It is frequently called prevalence rate, but we will see that the rate is best used for a different kind of measure. But remember, it is a proportion, 0 to 1. It's okay? Then you have the other measure of disease frequency, which is, question for you. Beyond prevalence, you have Can you hear me?
Yes, of course, we hear you.
Okay.
Yes, yes.
Okay. You have prevalence.
Prevalence is 0.3.
Sorry.
Oh, sorry, I was confused.
So beyond prevalence, you have incidence. It's okay? But incidence is ambiguous term. You have two incidents. So the first is cumulative incidence, also called risk. For simplicity, we call risk, which is the number of new cases, not existing cases. So if you take this year, a person who had cancer 5 years ago, which is still in the population, will not be counted in an incidence study. Only subjects diagnosed this year. So new cases or deaths, which are always new, in a given population, in a given period, divided by the population without the disease at beginning, so T0. Synonyms are cumulative incidence, incidence proportion, in infectious disease attack rate. If you look at mortality among disease, you have case fatality risk or case fatality rate. It's a proportion, goes from 0 to 100%. And you have to specify the period. because, for example, my risk of dying before the end of the lecture is very small. My risk of dying the next 10 years may be appreciable. Okay. Example of risk, mortality among all people with SARS is greater than 50%. The lifetime risk of dying from lung cancer is 10%. Here is implicit that we are talking about an infectious disease, so the time is a few days or weeks. Here you have lifetime risk. An example, I don't know if you use in your countries the cardiovascular risk in 10 years. So cardiovascular risk, low, etc., or beyond more than 30%, very high. So the colors indicate the risk level. And these are examples of men, non-diabetics, cardiovascular risk in 10 years. You have non-smokers, smokers, the cholesterol level here, the systolic blood pressure here, and based on this combination, you have a low risk or a very high risk. It's okay? You specify in 10 years. The last type of measure of disease frequency is the incidence rate, or if we talk about death, mortality rate, which is the number of new cases or deaths in a given population. So the numerator is the same of risk, but denominator is not the population at the beginning, but the population time at risk. So you have time inside the formula. So synonyms are incidence density, force of mortality or morbidity. When you say rate without specification is implicit, that is an incidence or mortality rate. It takes into account not only whether a disease occurs, but also when occurred. And the best way to view incidence rate is to regard it as speed, velocity. It's a speed of disease in a population. So for velocity of a car, speed of a car, you have kilometers per hours. Here you have cases, disease person per hour, week, year, and so on. So rate can go from 0 to infinity. For example, you may say lung cancer incidence rate in Italy is, it was in some part, this number now is lower, but just as an example is 100 per 100,000 person years. To explain this, you may say, to communicate this, you may say every year in 100,000 people, 100 get lung cancer. So you are always to say every year, every month, every week, and so on. So this is the speed of population. Все хорошо?
Yes, да, хорошо.
Yes.
Да.
Let's go to Sorry, a question for the organizer. Do we have should we have a pause or we can continue?
As you wish. I think we can ask from our participants if they would like to have 5-minute breaks, or we can continue and finish for 5 minutes earlier. It's up to you.
Okay, 5 minutes break.
Yes, break, please.
Okay, so 5 minutes, we are back.
Thank you. Dear participants, if some of you have some problems, please try to reconnect by the same link, okay? And I know all of these problems. I received all your messages in the WhatsApp. We'll decided we'll solve this problem later after lecture, okay? Thank you very much and have a nice break for 5 minutes. I will meet at 12 after 5 minutes at I don't know how much. Here it's 12:11. We'll meet again. Thank you.
Okay. Are you there?
Yes.
Okay, let's look at a simple example and calculate the risk and rates. Imagine a study of 5 individuals who are followed up for 10 years to record tumor occurrence. This is cancer. This is loss to follow up. Sorry, it's in Italian. Beginning of observation, end of observation. Which type of study is this? Imagine the 5 individuals are exposed to a pesticide. It's a cohort, case control, or cross-section. Can you hear me?
Yes.
Yes, we can.
Okay, which type of study is this?
Cross-section.
Be careful. You have 5 individuals. You followed up for 10 years. You follow up the 5 persons.
Cohort study.
Okay, so if there is follow-up, it is a cohort study. It's okay?
Yes.
Okay.
Cross-section, when you
I think it is not cohort study. It's, I think it is not cohort study. Case control study.
No, remember, a case control study, you start with exposure or with disease. In a case control study, you start with disease. So you take cancer cases, non-cancer cases, and you ask something to them. Here you have 5 individuals. You followed, exposed, let's say, to anything. And you do the follow-up and record disease. So this is a cohort study. It's not, you didn't start from disease. It's okay? Хорошо?
Хорошо.
Okay. So imagine, so you have 1, 2, 3 cancer cases during these 10 years. So you have 3 cancer cases. What is the cancer risk in 10 years? The numerator is number of new cases. So it's 3, and denominator is at the beginning, how many they were?
5.
10 years, maybe.
No, the number of people at the beginning is 5, okay? So 3 divided by 5 is the risk. 60%.
Okay.
Okay. to calculate the incidence rate, we take the same numerator, 3, and the denominator are the person time, is the person time experience. So person years. How many person years do you have in this cohort of 5 individuals? You have to count the follow-up time. How many years was this individual observed?
8.5 or 8. Yes.
Okay,
Exactly.
8. This one?
10 years.
10.
They still okay. 10.
This
It was 5.
about 5.
5.
This let's say 2. It's even
2.
31.
This okay, was lost follow-up, but it was observed. You know that until here he didn't die, he or she didn't die. So 5 years. So 8 plus 10 plus 5 plus 2 plus 5, 30 years. It's okay. So the incidence rate of cancer is 3 divided by 30 years. That is 0.10 by year, or you may say 10%. Every year, there was a 10% cancer incidence. Okay. So this is with individual data. Now you have a cohort. You have name and surname of patients. Imagine I work with the Lombardy mesothelioma registry. I take care of the data. I analyze the data, not take care. So imagine in this period, we recorded this number of new cases, new diagnoses of mesothelioma, so-called incidence cases, so new cases. For simplicity, assume the Lombardy in this period had 10 million people, constant. What is the average incidence rate? Numerator?
6,700.
Is 1. Okay. 6,700. This is the numerator. Denominator? Remember?
10 million.
Denominator, population time. Okay. So denominator is population is how many?
10 million.
10 million. 10 million.
Okay, but this is not enough. Time, how many years?
17 years.
Be careful.
170.
It's a bit tricky because when you say 2000 included to
18, yes.
18. Okay, because implicit is that the year is included. So 18. So denominator is 10 million times 18. Because every year you have 10 million people. The cases have been recorded in 10 years. So both numbers should refer to the same span of years. Okay, now in a short time, we will see the calculation. A risk, what is the risk in this dynamic population? I help you. We cannot calculate it because we don't have the population at the beginning. We simply have, every year we have 10 million. It's not a cohort. Here we had 5 at the beginning. Here there is no beginning. There is no cohort. It's a dynamic population study. So a registry is built in a geographical cover, a geographical area. So basically, the study base is the population which changes every day. Okay. So the incidence rate over that period is this multiplication. It's a small number, 0.00003. Difficult to communicate than to understand. But usually you multiply per million or per 100,000. So you can say 37 per million person years. So every year, in 1 million of person, 37 get mesothelioma in this region. Or every year, in 100,000 people, 3-4 get mesothelioma. Okay, so in a dynamic population, you cannot calculate risk because you don't have the population at T0. But there are formulas to calculate it. You will see also in the chapter, there is a short description. I would skip this, but because there are 3 formulas, the best one is this. But remember that rate is speed. Speed per time is space. So the similar concept. If you multiply the speed by time, you have the risk. Okay? So the concept is, if you have a dynamic population, you cannot calculate the risk, but you can calculate the rate, and from the rate, you can calculate the risk. It's okay? We skip this. So the rate is better because you can calculate either in cohort, either in dynamic population study. Risk only if you have a cohort. Все хорошо?
Yes, yes. Mm-hmm.
Okay. Oh, sorry. There is another. I found a nice example in an old book, epidemiology book by Austin Bradford Hill, who was an eminent statistician in UK. The first clinical trial was made by him. He discovered that smoking causes lung cancer and many other things. There, in this old book, there is a nice illustration of which a simple example of which say that the rate is better. So let's take this example. Suppose we are in January 1st, 54. There are 5,000 persons to be vaccinated. 300 are vaccinated on April 1st, 600 on July 1st, and 100 on October 1st. So at the end of the year, there are 1,000 vaccinated and 4,000 till unvaccinated. During the year, we registered 110 attacks, so infectious diseases, among the vaccinated, and 890 in the non-vaccinated. Suppose you didn't follow an epidemiology course, you only know proportion, and the question is vaccine effective? Is this vaccine good? So the intuition will be to calculate the risk, the proportion of infected in vaccinated, which is this number divided by this number, which is 11%. And to calculate the same in a non-vaccinated, this number divided by 4,000, which is 22% about. Okay? So if we take the ratio of this and this, we have the so-called risk ratio, which is about 0.50, 50%. So if we follow the intuition, we would say that this vaccine is good. It reduces the frequency of infection by 50%. 50% efficient, effective. It's okay?
Yes, sir.
Okay. Now you follow the epidemiology course. You know that there is another measure, which is the incidence rate. Let's calculate the incidence rate. Numerator are the same because the numerator is the new cases, which is exactly this and this. But the denominator is the person time under observation. Okay? To help you, it is easier. This. When we follow the intuition, we don't take into account time. Vaccinated subjects were unvaccinated before being inoculated. This is obvious, but you have to introduce this in the calculation. So take the 4,000 never vaccinated. There is no ambiguity in saying that they are always non-vaccinated. Take the 300 that were vaccinated on 1st of April. These 300 for 3 months were non-vaccinated, then were 9 months vaccinated. It's okay? The 600 were 6 months unvaccinated and then vaccinated, and the last 100 were 9 months non-vaccinated and then vaccinated. So to calculate the denominator for vaccination no, you have to sum all the red lines. So 4,000 people for 1 year is 4,000 person year. Okay. This part is 300 times 1/4 of year. This part is 600 times half of year, and 100 for 9 months. That is 9/12, 3/4 of year. It's okay? Do you follow the reasoning?
Yes.
Okay. For the vaccinated, similar thing. These 300 were how many person years? 300 by times 3 divided 4. 600 times 6 divided, 2 divided 4. 100 times 1/4. And this is the calculation. So if you do this way, you discover that you have 110 divided 550, that is 0.20 per year, or 20% per year, and here 20% per year, exactly identical. So if you do this way, which is the right way, you discover that this vaccine is not useful. It's okay? So incidence rate is better because it's easy to deal with time varying exposure. There are many time dependent variables in the life. Here I reproduced the chapter so those who are interested can read. But this example is contained in the chapter, which is common fallacies and difficulties. And this is an example of neglect of period of exposure to risk. So it goes with the calculation, fallacious, wrong comparison, true comparison. Okay. Finally, we remember that this distinction is between risk and rates is very old. William Farr, which produced the first life tables. Sorry. Made a distinction between cholera and tuberculosis. Mortality from cholera was about 50%. Tuberculosis at that time almost all died. But the sorry, I cannot hear. And so he made a distinction between two ways of looking at diseases. Deaths out a given number of cases, which is the risk, which is this, which is higher for tuberculosis, and 2, in the force of mortality, expressed by deaths out of a given number of sick at a given time. You see the time is here. So this is the incidence rate. So tuberculosis was more dangerous, but cholera probably excited the greatest terror. Because when cholera came, like COVID, was very speed in provoking deaths. But just to tell you that rates are known since about 2 centuries, but many people do not know rates, do not know the existence of incidence rates. My colleagues in the hospital, who are physicians or nurses and so on, do not know, or biologists, do not know incidence rate. But rate is probably the most fundamental measure in epidemiology. It's okay?
Okay.
Okay, we already commented this. This example is an example of so-called immortal time bias. Immortal time bias, you see another paper, which is not very simple, but immortal person years, the experience of study subjects that is event-free by definition. For example, if a person was infected here, he wouldn't have been vaccinated afterwards. So to be vaccinated, you have to survive this period. So the correct handling of immortal person years, the correct assignment of each increment in person time of follow-up is to that same exposure category to which a death will be assigned should it occur at that time. This is in a paper of 1987, which deals on allocation of person time. So you have to think, if I was infected here, I will be vaccinated or not? No, not vaccinated. So this part should be attributed to non-vaccinated. An example of this mistake is my colleagues in Italy. They took patients with liver transplantation. So they followed up a number of subjects with liver transplantation to record de novo tumors. That is, cancer occur after transplantation. Which type of study is this? There is follow-up. Be careful. If there is follow-up, you don't have...
Cohort, sorry.
Cohort, correct. Dobrze. Okay, look at this graph. These are 2 Kaplan-Meier curves. Are you familiar with this? If not, I explain briefly. We have survival here. So by definition, we start, everyone is alive. So survival after liver transplantation. So, sorry, beyond calculating incidence of cancer, they calculated mortality after cancer. So everyone is alive at the beginning, then every step down is a death. The more you go down, the worse you are. So in this line, black continuous line, you have subjects without cancer. They were transplanted, they did not have cancer. So no ambiguity. It's like non-vaccinated, always without cancer. These lines represents those who had cancer. And you see a strange behavior here, because in about 50 months, so about 5 years, they were better than people without cancer. This is clinically nonsense. If you have cancer, you have a worse prognosis than people without cancer. So there is a mistake here. And the mistake was this. They consider subject with cancer always with cancer. But imagine you are transplanted here. You may spend 5 years without having cancer, 2 years, 1 year, 6 years, and then you have cancer. So they made the same mistake of not considering the time, and that cancer is a time-dependent variable. Yesterday I didn't have cancer, today I have cancer. Immortal time bias. If a person die without tumor, cannot go in tumor, yes. So this part is immortal if you consider wrongly. It's okay. You may have time to think about this, but it's a frequent error. Not so frequent, but it happens. I repeated just for exercise this mistake. I examined lung cancer mortality or survival after cancer recurrence. I made the wrong analysis. You see the crossing of curve, like here. And then I made the correct analysis, because the subject has a diagnosis of lung cancer. He or she may never have recurrence, so always 0, no doubt. But some people have a metastasis or local recurrence of lung cancer. So for some period, they are without recurrence, and then they are with recurrence. It's okay?
Yes, sir.
So this is a paper we made in our hospital, same topic, but you see that the curves are well separated. This type of mistake re-emerged in the last 2 years with COVID-19. So this commentary is biases in evaluating effectiveness of drugs for treating COVID-19. And they say immortal time bias is common in core studies of drug effects, and systematically biases results downward in favor of the treatment. No, it's like the example of vaccine before. You exaggerated the effect. The vaccine had no effect, but you, with the wrong analysis, you found that there was a 50% effectiveness. And the concept is always this. Patient 1 at the day, let's say 16, begin to assume hydroxychloroquine. So in this moment, assume chloroquine. If you consider patient 1 as always being treated with hydroxychloroquine, you do an immortal time bias. The same for patient 2. Okay. Again, a recent editorial from researcher from Iran. Same argument. In current random of follow-up times in terms of exposure status, may introduce immortal time bias in favor of the exposed. The paper is not so easy, but the message is clear. What to avoid immortal time bias, you have to do time-dependent analysis. That is, use incidence rates by allocating person time in a correct manner. The problem here is that you take away person years from the treated, for the untreated, and you give it to the treated. So you make two errors. Removal of the immortal times from the unexposed. The second is adding them to the exposed person time. In this example, you made a gift to the vaccinated this period and subtracted to the unvaccinated. The same here, you made a gift to the vaccinated, you gave them time, immortal time, so the rate, the risk was lower, and you subtracted to the unvaccinated. If you exclude this part, sorry. Okay. In the case, if you exclude some periods before treatment, the error is only one-fold. You subtract, but do not add to the other. Both biases can be remarkable if prevalence of exposure is high or outcome incidence is low. Okay. Все хорошо until now?
Все хорошо. Okay.
Okay. Just an example of, again, on incidence rate and risk. This is the first randomized control trial or Pfizer vaccine. Called BNT162b2. Okay. So the conclusion was that 2 doses of this vaccine confer 95% protection against COVID-19. How do you calculate efficacy? Efficacy is called in a randomized clinic control trial. In real world, it's called effectiveness, but always BE. vaccine efficacy or effectiveness. Simply, you take 100, 1 minus incidence rate ratio, where incidence rate ratio is the calculated ratio of confirmed cases of disease per 1,000 person years. So from here, you understand they are dealing with rates. Okay. Just the picture to show these are vaccinated for 1 week or 10 days, 10, 12 days. They have the same cumulative incidence of disease. Then vaccinated flat down, unvaccinated continue to have infections. And this is the main table. Let's look at this. This is the same, but slightly different. COVID-19 occurrence at least 7 days after second dose in participants without evidence of infection before the start of the study. Here they included also a few people, some people who had already been infected, but they were vaccinated. So let's look at this. This is the number of the treatment arm, the number of control arm. In this case, since the two there is randomization, so you randomize and say Dario Consonni will take vaccine. His brother will not take the vaccine. The starting point is the same. The observation time is almost the same. So if you do 8 divided by this and this divided by this, these are similar, and you can obtain efficacy just calculating a risk. But what they did is the correct, even if it in this case identical, calculation. What is the incidence rate here? Surveillance time is that. So this is the denominator in 1,000 person year. What is the rate here? How much? Question for you. How do you calculate the incidence rate in vaccinated? Can you hear me? Can you hear me?
Yes, sir.
Okay.
We take 8 divided by multiplied 2.2, right?
Okay, perfect, perfect. And in the placebo group?
Same approach, 162 divided by the 18,000 multiplied by 2.2.
Okay, perfect. So this divided by this per 1,000, because here is 2.2 in 1,000, but in fact is 2,000. 3.6 per 1,000 person years. Here, 72 per 1,000 person years. So we can say that, so if we take this ratio, is the incidence rate ratio, like they did. Which is 0.05. So vaccine efficacy is 1 minus this times 100, because we understand better percentages, 95%. So we say that vaccine was now 95% effective. But what it means, this? I asked my colleagues, and nobody knows, because they are not epidemiologists, they are not statisticians. 95% means that vaccine reduce disease rate by 95% to 5%. Or we may say reduce 20 times the disease, because 1 divided this is 20. So to explain this to a person, you can say without vaccination, instead of 8 cases in the vaccinated, we would have observed 20 times cases, 160 cases. In this simple in the sense that since they start at the same moment, you can also look here, the same, approximately the same number of subjects. You see that 8 here, 162 here. So this is vaccine efficacy.
But I believe this will not work always.
Sorry?
I believe that this will not work all the time.
Sorry, I didn't understand. The audio is not...
So in this case, we see that the approximate vaccine effectiveness efficacy is 160. So comparatively to our data here, 8 and 162. So it's close, but this situation happens not all the time. In some cases, probably will be different, or is it same?
Okay.
Like ordinary.
This is the clinical trial. They select about 40,000 people, 20,000 vaccine, 20,000 placebo. In this experimental study, efficacy was very, very, very good. 95%. You would expect that when you use the vaccine, you have more or less the similar results. But it's necessary to do study in real population. For example, we did a study in our hospital. In the hospital, there are physicians, nurses, health assistants, and so on, so more exposed to risk and so on. I calculated efficacy of 83% about. So less, but all in in any case, very, very good. Are you doing vaccination in your countries? With what?
I don't know. I didn't control it.
No, but do you use this vaccine or other vaccines?
Of course. In Kazakhstan, people who are older than 18 years, they took vaccinated already.
Okay, but you took Russian vaccine or
There are different vaccines, Russian vaccines and China's vaccines, Arabic vaccines, and now the Pfizer vaccines come to us for children and for pregnancy women.
Okay. I imagine this similar in the country around Kazakhstan. Okay. So it's 1 o'clock. I will reserve this to. I think we will have other lectures. I will stop here. If you have question, I can answer. If not,
dear participants, if you have questions, please don't hesitate to ask Professor.
I have one question, dear Professor. How we don't confuse when we measured something, for example, if it's a panel study, or sometimes it can be confused with cohort study, yes? For example, when we measured something 3-4 times for one group people, and okay, there will have to be 2 groups, yes, in cohort study, who are underexposed and who are without exposure, yes? In panel studies, there are only 1 group, yeah?
Not exactly. For example, take a factory in which all workers are exposed. It is a cohort of exposed people. Then you will have to find a comparison group. But occupational epidemiology studies usually are composed of a cohort of exposed people, unless you have some information. For example, a manual worker was exposed, an office worker was not exposed. But you may also have everybody exposed, and the task will be to find a suitable comparison group, which usually is the general population. A panel study so in a cohort, you take people, you have a list of people you follow for many years.
Okay.
Imagine a repeated cross-sectional study. You do a study in 2020. There are 1,000 people, 100 people. Then you do the same study 2 years after. Maybe the 10, you have 100 people, but maybe they're not the same. Someone went away, someone get into the factory. So it's not necessary the same. So in this case, if it's not exactly the same subjects, it is called repeated cross-sectional study, so panel study. And usually you do this, for example, because you ask about symptoms, respiratory symptoms, musculoskeletal symptoms, you do biomonitoring, and so on. Cohort studies are best used for accidents or disease occurrence. I don't know if I was clear enough.
Okay, thank you.
Пожалуйста. Other question or? If not, just 2 words about, I sent you a chapter in the Claudio Colosio book on pesticides. I wrote the chapter after I was in Kyrgyzstan in 2018. So I had basically students from that area in mind, but look, here is the same situation. So I prefer start from the very basic building bricks of epidemiology. Then it's easier to understand difficult things. So if you have time, you have a will, you like, you can give a look at the chapter. Of course, there will be people with strong interest in epidemiology, others are less interested, so it's up to you. The chapter is long. There are some parts difficult towards the end, but it's less than a book. So it would be better to have a book, but this is a good compromise. So if you don't have question, I tell you spasiba in different languages. I forgot some language, I think.
Thank you very much, Professor, for your interesting lecture. Yes, for example, in my point of view, I agree that we should start from basics, just for somebody to remind, and we have some new changes in epidemiology. Not that crucial, but some of them might be changing. Thank you very much one more time for your time, for conducting the lecture, and I hope we'll have another lecture with you. Yeah, and to participants, I would like to say that if you don't mind, we'll stay for 5 minutes for discuss about the technical problems and other problems which we face it today and in general. So,
okay.
Grazie.
Okay, thank you. Thank you, Professor.
Большое спасибо. До свидания.
До свидания.
Goodbye.
Thank you very much. Goodbye.
And okay, dear participants, if you don't mind, I will switch into the Russian to speed up our time because it's already late. I mean, means that you have another commitments. Дорогие участники, если у вас были какие-то непонятные вопросы, либо вы желаете оставить отзывы, вы, конечно, можете написать письмо с благодарностью, либо нам будет приятно К тому же это будет еще одним доказательством о нашем прогрессе для Erasmus офиса, поскольку у нас недавно, кстати, это объявление и обращение. Недавно мы участвовали в мониторинге Erasmus офиса в Узбекистане, в Казахстане, где мы получили несколько конструктивной критики, в котором говорится о том, что мы должны распространять наши лекции, также, точнее, делиться нашими лекциями с другими университетами, которые заинтересованы. То есть это сообщение о том, что вы можете поделиться ссылкой на будущие лекции с теми лицами, с теми университетами, с теми педагогами, либо профессионалами, коллегами, которые заинтересованы именно в той тематике. Но прошу соблюсти небольшую ограниченность, поскольку мы сейчас как раз перейдем к нашей больной теме, поскольку, возможно, мы попросим одного либо двух представителей из университета, не больше. Плюс вы можете поделиться с данной ссылкой, с будущими ссылками для лекций, для встреч с офисом, с вашим местным офисом, Erasmus офисом. То есть Erasmus офис в Кыргызстане, в Казахстане, в Узбекистане и в Таджикистане. Вот, поскольку некоторые из вас еще ожидают мониторинги Таджикистан, Кыргызстан, и, скорее всего, данная критика тоже поступит в адрес. Надеюсь, не поступит, но никто не знает. Теперь, самая главная и больная тема – это Microsoft Teams сегодня прошел не совсем удачно, как мы ожидали. К сожалению, мы приносим большие-большие, глубочайшие наши извинения, особенно тем участникам, которым не было слышно, не было видно, не смогли подключиться, либо подключились с 10-го раза, поскольку еще хотелось бы сказать, что это из-за нестабильного интернета в Центральной Азии, поскольку я сама, когда была в Центральной Азии, подключалась к институту Италии, то у меня тоже точно такие же были проблемы. Я это отлично понимаю, и, к сожалению, сегодняшняя очень интересная лекция прошла в таком формате, но будет запись доступна. Кстати, я сейчас запись остановлю, поскольку это неформальное обсуждение. Сейчас я секундочку, я остановлю запись. Окей. Теперь по поводу записи.